Okay. Tonight's topic, we're going to be talking about capacitance and inductance. In the past, all we've been talking about is resistance and, of course, current and voltage and the reaction through resistance, which verifies Ohm's law and the laws of series and parallel circuits. And now we're going to add a couple more elements to the group, a capacitor. And a capacitor is two conductors separated by an insulator. Now, that being said, how much current could flow through a capacitor? Well, obviously it would be zero, because if it is two conductors separated by an insulator, there is no current path between the two conductors. That is true once the capacitor is fully charged. So once the capacitor is fully charged, as far as being in a circuit to analyze the circuit, it's considered an open circuit since no current can flow through it. However, a voltage will be developed across it. Now, during the charge time, the capacitor acts as a short. And the charge time is considered to be fully charged once 5 time constants has passed. A time constant for a capacitor circuit is the resistance times the capacitance. The unit of measure of capacitance is farads. Usually it would be microfarads or picofarads. A farad is a fairly large unit of measure. A capacitance is equal to the charge divided by the volts. Now, charge is kind of like current. It's actually not current, but it's similar to current, and we'll see how we can make that similarity when we do a few calculations after a while. And 1 farad is equal to 1 coulomb of charge deposited on the plates by a potential difference of 1 volt across the plates. It's also equal to a constant, which is 8.85 times 10 to the negative 12, times the relative permittivity, and that is the inherent characteristics of the dielectric, and that's what we call the insulating material between the two plates. And it can be anything from air to paraffin-coated paper to mica, whatever it is. Okay, so those two multiplied together times the area of the plate divided by the distance between the plate, which is actually the thickness of that dielectric material. And then, of course, we can take a capacitor and we can connect them either in series or in parallel in our circuit. If they are in series, to find the total capacitance, we take the product divided by the sum. If they're in parallel, we just add them together, so we have the sum. Just backwards from the way that we calculate total resistance. Now, I didn't really put a whole lot of material on that first slide, but I spent quite a bit of time covering all of this because one of the inherent things about a capacitor is the fact it has the ability not only to accept this charge, and once it's fully charged, you have no current flow through it, but you do have a voltage potential across it, but it has the ability to store that voltage until there is a path from one of the conductors over to the other conductor. So as long as there's no path there, it will remain charged. So I could charge up a capacitor and very carefully take it out of the circuit and set it down on the desk. It's still fully charged. And I could come back a year later and it's still fully charged unless it becomes discharged by a path from one terminal to the other terminal. So that's one of the things about a capacitor that's different than that of a resistor. I also would have several different capacitors that I would pass around so that students could see the size of them. I'd talk about the difference between a electrolytic capacitor or polarized capacitor and then just a standard capacitor. A electrolytic or polarized has a distinct positive and negative terminal. And if you put them in backwards, depending on the conditions, they could actually explode because if the voltage is high enough, they would actually burst. And when they do that, they make quite a noise. So we have to be very careful when we're talking about electrolytic capacitors. Most capacitors are a fixed value, but they do make variable capacitors. And kind of giving away my age here, if we talk about tuning a radio, for example, and tuning it into the radio station, that tuner, you're dealing with a variable capacitor. Okay. Capacitors are used to develop timing circuits, any type of a circuit that has a timing function to it. We use a resistive capacitance network, and that gives us our time constant in order to fully charge the cap. One example of this that I use is the delay action in your windshield wipers on your car. That is a capacitor timing circuit that is in there to give us that time delay when you're on the mist cycle. Okay, now, this next one, I'm going to put you guys to work here. Let's figure out what the total capacitance is of these two little circuits that I've drawn here. Okay, in this one we have 3 microfarads in series with 6. What would that be? Well, we have to do product over sum. So that's 3 times 6 is 18. Divided by 3 plus 6 is 9. 18 divided by 9 gives me 2. That 2 is in parallel with that 7, which means we add them together. 2 plus 7 is 9. Now, if I take that 9, all that is in series with 0.2. So product over sum, 0.2 times 9 divided by 9.2. And I come up with 0.195. Very close to the 0.2 because 9 is so much larger than 0.2. But it will be smaller than the smallest one in the group, but in this case, just a slight bit smaller. And this one down here, we have, starting out here, I've got 10 in parallel with 30. So we'd add those, that's 40. In series with 60. Product over sum. 40 times 60, that's 2,400. Divided by 40 plus 60, that's 100. 2,400 divided by 100 would give me 24. And then that 24 is in parallel with the 20. So we'd simply add them together, giving me 44, and it's picofarads this time. Everything is picofarads. Okay. The charge on a capacitor is equal to the capacitance value times the voltage. Now, the energy that is stored by a capacitor, measured in joules, is equal to 1/2 times the capacitance value times the voltage value squared. That's in terms of voltage. If we're in terms of the charge on the cap, then the energy stored is the charge on the cap squared divided by 2 times the capacitance value. Okay, now we're going to take a look at this circuit, and notice we are applying DC. Now, I need to give you just a little bit of background on what's included in the DC courses at the college level. When we first developed the tags, which is going from college to make sure there's continuity from one to the other, we started that process probably 15 years or so ago, maybe a little longer than that now. And a lot of the institutions within the DC course, they covered up through what we have done so far, which gets into the series parallel and the mesh analysis and Thevenin's and max power transfer, Y delta, delta Y, and so forth. And then they also included capacitance and inductance, but a lot of them only looked at just with DC applied, steady state. They did not get into the charging cycle until they got into the AC course. But then several of the institutions included the charging cycle, which is the exponential rise of the voltage across the cap and the exponential fall of across the resistor. And so that discrepancy had to be ironed out, and the decision was made that everybody agreed to that the charging cycle would be included in the DC course. And now that we're dealing with C-tags, which is at the Career Tech Center to the college level, then we also have to include that in your course as well. And then when they get into AC, most institutions start with looking at capacitance and inductance with the AC voltage applied rather than a DC voltage applied, but they already have a background in capacitance value, total capacitance, and the exponential charge and discharge of the cap. Okay, looking at this one, again, we're looking at steady state, and we are going to not worry about the charging cycle yet. We'll get to that in just a couple of minutes. Okay, let's find the voltage across C1. Okay, C1 would be 10 volts because it's in parallel with the 10-volt source. So I got 10 volts from here to here, got 10 volts from here to here, also have 10 volts across C1. The charge for C1, 6 microfarads times 10 volts is 60 microcoulombs. Now, if I look at this flag in the middle, I've got 6 microfarads in parallel with 12, or excuse me, in series with 12. 6 in series with 12. Treat them as if they were resistances in parallel. It's product over sum. 72 over 18 gives me 4. So the equivalent capacitance is 4 right here. Okay, the charge, Q for C2 is equal to the charge for C3, which is the capacitance value, the 4 microfarad times 10 volts, 40 microcoulombs. Now let's look at the voltage across C2 and C3. The voltage for C2 would be the charge of C2 divided by C2. 40 microcoulombs divided by 60 microfarads is about 6.67 volts. And for C3, the voltage would be the charge, which was 40 microcoulombs, divided by C3, which was 12 microfarads, that gives me about 3.33 volts. Now, those two together should be equivalent to 10 volts. Okay, so we got 10 volts from here to here, and we would have that 10 volts divided. C2 is 6 2/3, and C3 is 3 1/3. And then I did the energy stored by, I just did for C1. Okay. So that would be 1/2 times 6 microfarads times the 10 volts squared. And I come up with about 300 microjoules. Okay. Now, you guys can give me a little feedback. Do you normally cover capacitance up to this level at the Career Tech Centers?
Indeed, indeed we do, or at least I do.
Okay.
And I think we even go into the charging cycle where we're starting to talk tau.
Yeah, that's coming up. Yeah.
Yeah.
And that's good, because that's where we're at with the DC cord.
Okay. Yeah, some of the other stuff that you dealt with last week, the mesh analysis, those kind of things we haven't touched in the past.
Mm-hmm. Okay.
But it's good to know it's out there and that's what's needed.
Right. Okay, anyone else?
Yeah, we do it. I do it at my school too, and
good.
I go through inductance.
Uh-huh.
So, I have to. It's in the textbook. It's not really that difficult to go through it with the kids.
Okay. What about their math levels? Do you find them doing okay with the exponential function?
The kids I have who are going to CTAG, now my math levels vary because I teach at the senior level, so some of my students are in Algebra 2. I have others in AP Calculus. So
okay.
So my CTAG kids are typically the kids in pre-calc or AP Calc, and they handle it just fine.
Okay.
The other students probably aren't going to CTAG out unless they see quite a bit of improvement.
Okay. Yeah, that's been an ongoing thing locally in Southern Ohio for us. Most of the career tech centers, I'm going back, say, 5 or 6 years ago, it was always a problem with the math level. But over those years, we've really been working with them to pump up that math level, and they seem to be doing much, much better now.
Well, I'm in a comprehensive high school, so and we offer an honor section for our engineering technology starting this year.
Okay.
So we've attracted a lot more kids who are a little more math competent than I have in the past.
Right. Sounds good. Okay. Now let's take a look at capacitance with reference to the charging cycle. And again, this particular handout is repeated a little bit there at the beginning. But now we introduce tau is the RC time constant, and I give you the symbol for it. It's the total resistance times the total capacitance. And then the percent table of change for VC. Within the first time constant, the cap's going to charge 63.2%. And then the next one, another 23.3. The next one, 8.6, 3, and 1.2. And so on. After 5, it's considered to be fully charged. If you add all those up, it's very nearly charged. And then we have our actual equations here. The voltage for the cap is equal to my applied voltage times 1 minus e to the minus x. Now keep in mind that x is actually minus t over tau, the actual time over the time constant. And then for the resistor, it is your voltage times e to the minus x. And for current, it is the maximum current, okay, times e to the minus x. We've got exponential growth on the cap, exponential decay on the resistance, and an exponential decay for the current. Time is in seconds, and the time constant of the circuit is also in seconds. Okay. Now, these are for charging, and now we've got the discharging cycle, and VC is equal to E, your voltage times e to the minus x. Voltage for the resistor is the voltage times e to the minus x, and the current is I max times e to the minus x. Okay, now I'm going to scroll all the way down to the very last screen. And I have a picture of RC transient waveforms looking at that exponential rise and the exponential decay. And this is that for an inductor, which we'll get to. So that's on the very last page, which I include those in the handouts that I would give to students as well. All right, let's get back up here where we left off. Okay, I think that's pretty straightforward. This information comes from their textbook. They can highlight it in their textbook. They can write it in their notes. I give it to them on handout, and then we're going to do lots of exercises with it in the classroom. So they get pretty accustomed to using this. Okay, here's the first problem dealing with the capacitors. Given VC is equal to 60 millivolts times 1 minus e to the minus t over 5 milliseconds. Okay, so what is my time constant, tau? That's what's right here. That's my 5 milliseconds. So tau is equal to 5 milliseconds. Then I want to know what is the voltage at a time equal to 2 milliseconds, and then what is the voltage at a time of 100 milliseconds. Well, at 5 milliseconds is my time constant is considered fully charged, and 5 time constants, that'd be 25 milliseconds, is going to be fully charged. So I know this one, it should work out to be that it's fully charged, and we'll check that out in a minute. And up here, in 5 milliseconds, which would be the first time constant, it should be about 63.2% of the applied voltage. But this is less than 1 time constant, since we're only dealing with 2 milliseconds. So let's see what we come up with. Okay, on this one, VC is equal to 60 millivolts times 1 minus e to the minus 2 milliseconds over 5 milliseconds, which would be to the minus 0.4. Okay, and when we do that, I come up with 0.670. So 60 times 1 minus 0.670, that's 60 times 0.33, and I come up with 19.8 millivolts. Okay, I think that's pretty straightforward. And from what you just told me about the math background of your students, I think they can handle that with no problem. And then here's the one where we've got our time is 100 milliseconds over 5. Here we're raising it to the minus 20. So it's 2.06 times 10 to the negative 9, which is, might as well say 1 minus that. Okay, so we end up with 60 millivolts times 1, which is, for practical purposes, 60 millivolts. Now, granted, theoretically, it's never fully charged because it keeps getting smaller and smaller and smaller. But for practical purposes, it is fully charged because it's well over 99.9% charged. Okay, any comments, questions? These problems that I'm going over is actually some homework problems that I just pulled out that I gave last time I taught this. Okay, given VC is equal to 12 volts times 1 minus e to the minus t over 20 microseconds. Now my tau is 20 microseconds. Determine the voltage VC at a time equal to 10 microseconds. And then the time for VC to reach 6 volts. Okay, VC is equal to 12 volts times 1 minus e to the minus 10 microseconds over 20 microseconds. And that would be raised to the 0.5. Again, 0.607. Here we've got 0.293. We come out with a total of 4.72 volts for part A. Now for part B, now we know that our voltage is 6 volts. That's VC is equal to the 12 volts, which is your supply, times 1 minus e to the minus t over tau, tau being the 20 microseconds. So we just keep cranking through the algebra here. And at this point, we've got 0.5 is equal to e to the minus t over 20 microseconds. And here, depending on how your calculator's set up, you probably have to use the LNT, the natural law of 0.5 is equal to 1 times, or the log e to the minus e raised to t minus t over 20. And I come up with negative 0.693 is equal to minus t over 20. And then from that solves for t. And we come up with 13.86 microseconds. Is the length of time it would take for the voltage across the cap to reach my 6 volts. And again, I work with the students in whichever way, if they need to enter that in their calculator, I make sure that they're able to do that. Okay, any comments to this point? How about your students? Do you feel confident that they can do that?
Yeah, this is my first year teaching it to these guys, so it's we haven't got the capacitance yet, but
okay.
Yeah, they'll be able to do it.
Okay.
Yeah, some of mine will struggle with this kind of stuff. They don't have quite as strong a math background.
Mm-hmm.
Some of them are doing okay.
Yeah. Okay, this next one that we have, this is just a toggle switch up here, the very top of it kind of got skewed a little bit as it went through the scan. So we've got an 80 volt source, we've got a toggle switch, we've got 8 K ohms in series with C1, which is 6 microfarad, which is in series with R2, which is 12 K ohms. And we are looking for the time required for VC to reach 60 volts. Now, other words, the instant we close the switch, we start timing it, and we want to know how long it's going to take for the voltage across the cap to reach 60 volts, even though we're applying the 80. So let's find our time constant. Time constant is your total resistance in your charging loop, which is R1 plus R2. That's 8 plus 12, that's the 20, times the capacitance, or the total capacitance, which in this case is just 6 microfarad. That's 0.12 seconds. Then we're just using the same equation we've been using all along for the charge cycle. VC is equal to your voltage times 1 minus E to the minus T over tau. Plug in what we know, 60 volts here, 80 volts, 1 to the minus E to the minus T over 0.12 seconds. Go through the math. We come up with 0.25 is equal to E to the minus T over 0.12 seconds. So then T would be 0.12 seconds times a negative 1.39. That's negative as well, which gives me positive at the end. I end up with 166.8 milliseconds. This one, we made it just a little bit more difficult because we got K ohms, microfarads, we're going with seconds here, and we end up with milliseconds in our answer. So they got to play with the decimal points a little bit. And then I said, okay, what is the current when VC is equal to 60 volts? So now we're looking at the current. IC is equal to E over R times E to the minus T over tau. Those are those equations that we had earlier. 80 volts divided by 20K times E to the minus. Now we know what this is. Our time is 166.8 milliseconds over tau, which is 0.12 seconds. So that's 4 milliamps. This gives you current, voltage divided by resistance. That's equal to times E raised to the minus 1.39. Number 249.08 times 10 to the negative 3 times 4 milliamps, which I rounded slightly here to about 1 milliamp. So that gives us an example dealing with the current decay as well. And again, I stress with the students that with a capacitor, once it's fully charged, once the voltage has been applied and more than 5 time constants has elapsed, and the cap is fully charged, there's no current flow through the cap, and there is a potential difference in voltage across the terminals of the cap. Then I have the students do a little lab, and what we do is we take just a 6-volt incandescent light, just a little small lamp, and we hook up a power supply, and I put a cap in there, and I put a small resistor in series with it, and I have them apply a DC voltage to it. Actually, they're using a 9-volt battery. That's the purpose of the resistor. And I have them put a push-button switch in there. So whenever they push the switch in DC, nothing happens. the light does not come on. Then I have them change to a 9-volt AC source. And whenever they apply the AC, and they push the switch, you'll see the light. It won't be full brilliance by no means, but it will start to come on. And I ask them, how does that happen? That, we just said that current can't go through the cap, and it's in series with the bulb, so there's no current going through to that bulb. But in AC, the bulb tries to light. How's that happen? And, of course, I keep agging it on with them a little bit that it's magic and so on and so forth. And then I explain to them, and I actually draw a little picture on the board. I start off with, just picture this, a piece of pipe. You got water flowing through the pipe. Now we're going to put a rubber diaphragm in that pipe. Okay, now water cannot flow through that diaphragm unless you put enough pressure there that it punches a hole through it. Okay, so DC, we're simply pushing on the diaphragm and it distorts the diaphragm a little bit, stretches, and that's it. But there's no current flow through it. Now, same scenario, this time I'm going to first push on the top of the diaphragm, then I'm going to pull up on it and then push down on it and pull up on it and push down on it and pull up on it. You see the idea of the AC waveform? Okay. So I got a sinusoidal waveform going on the top side. Well, the bottom side, I've got the same reaction, but it's not the same current going through it. So current still does not go through the cap with AC applied. The effects of the current does, but not the current. Because if the current was going through it, it would have to punch through, in this case, our rubber diaphragm, but in the case of a capacitor, it would have to actually punch through the dielectric material. So that's how I explain to them how we use it in electronics. We call it coupling caps to couple the AC voltage, blocking caps to block the DC voltage, and then things start ringing a bell. Now, obviously, our students in DC, they haven't had electronics, they haven't had AC yet, but we're getting close to that because this topic would be during the last probably 3 to 4 weeks of the DC semester. And then when they come back the following semester, they start right into AC, and our students actually take AC and electronics at the same time, 2 different courses. So they're going to get this exposed to them, and then in the past, when I taught AC and electronics as well, I'd always make reference back to that. Remember back in DC in the lab when we did this or that and so on. Of course, now I'm not in that loop anymore. But, so that just give you a little anecdote of how some of the topics that's in DC, you're just kind of leading them up to the brink, but you're not letting them take a drink yet. And then in the next course, that's when they're going to start drinking, but you can always refer back to that and keep that continuity going. Now, in your case, you're going to end with the DC course, and then they're going to come into AC, and more than likely, whoever's teaching the AC course at the college level, they're going to make reference to what the students had in the DC course at the college level, which should be the same as what you guys have got in your DC course, because they're getting the same information. It's the same no matter where it comes from, and the students are treated the same. Okay, any comments, questions at this point?
I was going to say we do actually go into some of the AC topics and even digital. Ultimately, my course is digital electronics.
Okay.
So we take things a little farther, probably more broad, less deep.
Okay.
Which I can see where these C tags. We want to go deeper on each of the topics, I'm sure, than we're covering.
Okay.
Just one other question I would have, which is, And just going back to capacitors, you know, where do we? They provide burst energy, but what? Can you give me some examples of where you would use them, why you would use them? What, like, you mentioned the timing circuit for for your wipers, but what? I guess that's where I'm kind of stuck. You know, I don't really know. Yeah, I don't have a lot of real world examples of what this stuff does, what all the electronic components do. I mean, you can look at a computer and obviously they're there, but why? Why are they there in that specific spot? I don't have anywhere to tell my students.
Yeah, we also use them for filtering.
Okay.
When you're converting AC to DC, just a typical DC power supply. Okay, you've got ripple. If you was to look at that DC voltage level, you got ripple in there. So what we do is we use a capacitor to fill the gap so that on that ripple, when it's on that negative cycle, the cap's actually going to charge that up, and we end up with DC flatline coming out rather than a DC flatline with a little bit of ripple riding on it.
Sure, that makes sense.
That's how we filter that out. That's another application that we use them for. Like I said, anything that's a timing circuit. And then also give them an example, and this is an example where they're using a capacitor and an inductor because they're 180 degrees out of phase when you get into the phase angle in AC. All the orange barrels and orange cones that we see out on construction sites. Well, every so often, especially in a rural area where you don't have street lights, you don't notice this so much out on the interstate because there's enough lights that they don't actually put flashing those little blinking lights with the lantern battery on them. But out in rural areas, they do. Well, if you just hooked a battery up to that light with a flasher, you know, you'd be changing the battery every day. You know, one night you'd run the battery down. But what we do is we put up a circuit that's got a capacitor in parallel with an inductor so that the capacitor's charging, and as it discharges, it goes across the inductor, and then the induced voltage from the inductor charges the cap, and they just sit there and trade back and forth. Now, if you did not have any resistance, in an ideal world, you'd have perpetual motion and just go on forever. But since caps, inductors, the light itself, none of this is ideal. We still have to have a little bit of voltage to tickle it to keep it going. But now that battery, instead of lasting one night, will last a month or more before we'd have to put another battery in there. Because once we get it started, they're just sitting there trading energy back and forth. We also use capacitors a lot for motor starting and motor controls. If you've got a heavy load, we use a capacitor start motor, which shifts the phase, which gives you higher starting torque to get the motor started and running. And then once you get it running up to speed, through a centrifugal switch, a mechanism of some type, the capacitor actually drops out of the circuit, and then you've just got your applied voltage. Also, when we do, again, speaking in terms of more on the industrial side of motors and motor controls, power factor.
Okay.
Large induction motors have an inductive load, which gives you a lagging power factor. To do power factor correction, we put a capacitor bank of the same capacitive reactance that the motor has developed as far as inductive reactance, and they cancel each other out, and we're back to unity power factor, which makes us happy when we pay our electric bill. And we can do that up to a certain point with static capacitors, just plain old, big old heavy capacitor banks. But then once it gets to where that's not feasible to do that, then we would use a synchronous capacitor or a synchronous, it actually looks like a motor. In fact, it is a motor, but it puts out a capacitive reactance rather than inductive reactance on the line at the same time of the same value so that they cancel out back to unity power factor. And now, depending on where you're at, our students at Shawnee State, we go pretty heavy into motor and motor controls in the electromechanical program. Our DC, AC, and electronics and our digital course also serves in the computer engineering technology program as well. And in that program, they don't go into the motor controls and so forth. They go heavier into the programming and
sure.
so forth. So it depends on which area they're going to. But
okay, that's great, Ken. Yeah, that's I'm taking notes here, but yeah, it's fantastic. That gives me some stuff I can talk about and
okay,
with a little more depth.
Good. Okay. Any other comments or questions?
Ken and Terry, I'm going to run upstairs to my class to make sure everything's okay. Just call my cell phone if something comes up. Otherwise, I'll be back in a little bit.
Okay.
Thanks, you guys.
Okay, let's take a look at inductors. Flux density is equal to the magnetic flux in Webers divided by the area in square meters. And flux density is measured in Teslas. 1 Tesla is equal to 1 Weber per square meter. And of course, prior to this, it's in their textbook, and I talk a little bit about it, showing what an inductor looks like, showing the magnetic field aligned with magnetic flux. You know, we just take a regular bar magnet. We know that we have a north and a south pole, and these lines of magnetic flux make complete loops out and around from one pole to the other, and then through the magnet.
Hey, Ken.
Yes.
Hey, before I even teach capacitors and inductors, I usually go into a whole section on electromagnetics. Do you do that after your inductor?
I've done it both ways. I've done inductors first and then magnetics, and then I've done magnetics, then inductors, and I don't know which way's better. I've looked at the results of student feedback, and it's about a flip of the coin. I mean, I don't see where it really makes a whole lot of difference one way or the other.
Okay.
I know in this case here, you know, all of a sudden we're talking about magnetic flux and so forth. So, you know, I spend just a few minutes talking about magnetics, then I get into inductors, and I tell them, okay, as soon as we get through the inductors, then we're going to spend more time on magnetics, which that's what I'm going to do with this little mini series here. Next Tuesday is going to be our last session, and what I'm going to do is talk about magnetics and magnetic circuits a little bit, and then for the last half of the course, the last hour, what I thought I would do is I'm going to bring a couple of final exam questions in. My final exam is basically based off of one circuit problem to analyze. And it puts all this stuff together. We're going to have a series parallel circuit that's going to include having to do a Y delta or delta Y transformation. It's going to have resistors in it. It's going to have capacitors, inductors, and we're going to analyze the entire circuit. And what I plan on doing is just having it as a blank on the screen to start with, just the circuit. And we're going to work through it. So what I want to ask everybody to do is bring a calculator, pen and paper, and we'll just work our way through that, and that will kind of tie everything together, which is what I try to do at the last week or so of the class that I teach at the college level, and then, of course, their final exam. That'll give you an idea how we tie all this stuff together.
Okay. That sounds decent, yeah. I haven't done a worked problem like that with the kids, but that sounds like that's a, I don't know, I'm going to look at that for my semester exam.
Okay. Okay, we continue on here. Now, if we're talking about an electromagnet, the magnetic force is equal to the number of turns times the current, and the unit of measure is ampere turns. And then, of course, inductance in henries is 4 pi times 10 to the negative 7th times the relative permeability. In other words, the material we're dealing with, how good of a material is it to make a magnet with. We could have cast iron, sheet steel, just regular steel, and aluminum, whatever. And that would come from a table. Then times the number of turns squared times the area, and that would be the area of the core, divided by the length of the core. At this point, we're looking at, actually making the individual inductor, and then a little bit later on, we're going to look at just off-the-shelf inductors, putting it into a circuit, putting it in series, putting it in parallel, and so forth. Now, the voltage for the inductor is equal to the inductance in henries times the change of current over the change of time. Now, at this point, that's derivative, you're starting to get into calculus, which at the college level is not a problem. We don't do it in the DC course. In AC, that's when we start looking at the calculus. So what we're doing is we're just going to give this value and this value, not actually how to find the derivative of it. Okay, that comes in the AC course. Okay, the greater the rate of change in current through the coil, the greater the induced voltage. And then at this point, I explained to the students that as far as an inductor is concerned, there's two major rules you need to remember. Number one is that if I apply a voltage across an inductor, and then I remove that voltage, there's going to be an induced voltage that's many, many, many times greater than the voltage that caused it, and it's going to flow in the opposite polarity. And it's going to go through whatever path that it has. And that's why, for example, if you're using a relay, electromechanical relay, and you have that coil of the relay controlled by a electronic device, a transistor, you have to have a diode strapped around that coil, or the inductive collapse of that induced voltage will actually burn up the transistor. And then I use the example of your car. What is, looking at the ignition of your car, what's the voltage source that we have in your car? Well, you got a 12-volt battery. Okay. At the spark plug, how much voltage does it take to fire a spark plug? Well, a whole bunch. If you want to go back into the 70s, 60s, and 70s, it was about 35,000 volts. Now it's about 95,000 volts because we've got electronic ignition. What's in between there? What's in between that battery and the spark plug? You got a coil. What's a coil? That's an inductor. An inductor is a coil of wire. So what's happening is we're applying 12 volts to the inductor, but then when we remove that voltage, the path for our current flow is through the spark plug, which has that gap, and if there's enough voltage potential, it will arc through that gap, creating a spark, and that's exactly what happens. And in order to do that, we have to have an induced voltage that's many, many, many times greater than that which caused it, and that's inherent to that of a inductor. Well, what controls how much that induced voltage is going to be? Number of turns and the current. Okay, just like if you want to make a little electromagnet, I refer to students, remember back when you was in elementary school, along, 4th or 5th grade, and you take a nail, you wrap a little bit of wire around the nail, and you hook it onto a flashlight battery, and now you got an electromagnet, and you can pick up paper clips with it. Okay, how do I make that a stronger magnet? Well, I can use a bigger battery, or I can put more turns of wire on the nail, or I can do both. And once we have a stronger magnet, then if we're looking at it in terms of electrical, when we look at the induced voltage that's induced, it's going to be greater. Then we look at the energy stored in joules is equal to 1/2 times the inductance. Inductance is measured in henries times the maximum current squared. Okay. Now this next handout, or the next slide, inductance, unit of measure is in henries. An inductor is a coil of wire. Now, a while ago, we were talking about capacitors, and we were talking about power factor correction and so forth, and I mentioned induction motors, industrial induction motors. They get their name induction motors because they have a inductive reactance as far as the power that is required to drive the motor. Okay, why is it an induction motor? Well, what's inside an electric motor? It's a big coil of wire. You've got a field coil, and then you've got an armature, which also has a coil wound on it. So we got lots of coils, or inductors, inside an electric motor. That's what it is. It's a huge inductor. Okay, once 5 time constants, and a time constant is the inductance divided by the resistance. Now, with a capacitor, the time constant was the resistance times the capacitance. Here's the inductance divided by the resistance has passed. Once 5 time constants pass, the inductor will reach a steady state condition. And the inductor reacts as a short with current flow through it, with practically zero resistance and 0 voltage across it. Okay, if there is 0 resistance, what's the potential difference from one side to the other? It would obviously be 0. How much current can flow through this coil of wire? How much current can flow through a wire? However much you got. That's what's going to flow. The instant voltage is applied to the inductor reacts as an open switch because it cannot change in 0 time. I keep stressing with students, anytime you're dealing with capacitors and inductors, this exponential function, even though it depending on values, it can be in the milliseconds or microseconds, it's still not 0 time. It cannot flow. Current can't flow in 0 time. It does take time when you're going through an inductor. It's not like a straight piece of wire. But once that time constant has passed, which again, usually that time constant is in less than a second, it's usually in milliseconds. Once 5 of those have passed, then it is in a steady state condition. Okay. Then once the initial applied voltage is removed, an induced voltage with a magnitude many, many times greater and of opposite polarity than the applied will be induced across the coil. And then I show a picture of here's your 5 time constants. You have the same charging rate as you did on the cap, and here we're going with the current for the inductor. The voltage on the inductor is an exponential decay, and then here is the voltage across the resistor, which would be an exponential rise. Okay, questions at this point? Comments? Okay, now let's look at inductors in series and in parallel. If it's in series, it's just the sum. If it's in parallel, it's product over sum. That's just the same exact way you do resistors. So let's do this first one here. What would be my total inductance there? I know you can work this out in your head, so I'll let you feed me an answer here. Okay, start out here. So we got 6 in series with 6 would be 6 plus 6 is 12. Okay, now.
Yeah, so it comes out to be 4 Henry.
Okay.
2 and 3, 4.
Yeah, right here, you've got, that's 12, right? And then you got 12 and parallel with 6, that's 4. And then that 4 is in series with 6, which gives me 10, right?
Yes.
Yeah. Okay, now let's look at this one. They're all the same value, but the way we have them connected. Okay, now this one, I started right here. I took those 2. So I got 4 in parallel with 4 would be 2. 2 in series with 4 would be 6. Now I've got 6 in parallel with 4. Okay, 4 times 6 is 24 divided by 10 gives me 2.4. I come up with 2.4 Henrys. So what you get?
Yeah.
Indeed.
Okay. Okay, now we look at these equations. They're very similar to that for the capacitor. And tau is equal to the inductance divided by the resistance this time. Okay, we've got an exponential decay for the voltage across the inductor. The voltage across the resistor is an exponential growth, and the current is an exponential growth. And that would be what we'd normally refer to as a charging and discharging, even though that's not the correct terms to be using. Okay. Then we have, as the field, the induced voltage collapses, you have an exponential decay on the voltage across the inductor and the resistor and the current. Okay, let's work a couple of problems here. Okay, determine the current for the inductor at t equals 1 millisecond and then 100 milliseconds. And we're given the current for the inductor is equal to 100 milliamps times 1 to the minus e raised to the minus t over, this is tau, which is 20 milliseconds. So we plug in what we know here. And at this point, you know, minus 1 millisecond over 20, that's minus 0.05. E raised to that gives me 951.23 times 10 to the negative third. Okay, 1 minus that gives me this value here, 48.77 times 10 to the negative 3. Then times my 100 milliamps, I come up with 4.88 milliamps. So in 1 millisecond, my current is now 4.88 milliamps. Okay, now then, at 100 milliseconds. At 100 milliseconds, I should be looking at basically 100, because if my tau is 20 milliseconds, 100 milliseconds, that would be 5 time constant, so should be nearly the 100%. We plug this in, crank it out, I come up with about 99.33. That's very nearly the 100%. Okay, questions on that? Okay. In the lab, I have the students put together a model of an ignition system for the car. And what I use for a spark plug is an incandescent lamp, or not an incandescent, excuse me, a neon lamp. A neon lamp takes, the ones that I have in the lab, takes anywhere from about 60 to 80 volts to fire it. I give them a 9-volt battery, and they have to be able to fire that neon lamp. So they need a coil. Well, the ones that I have available for them is an 8 Henry coil. So the way they connect this, they take the 8 Henry coil in parallel with the neon lamp. Okay, then I have them take the 9-volt battery, which is going to be in parallel with the coil and the lamp, but between the battery and the inductor, the coil, I have them put a normally open push-button switch. So is everybody picturing in your mind how to do this? You got a 9-volt battery, negative terminal of that battery connected to one side of the inductor and to the other side, also to the neon lamp. Off the positive side, go to your push-button switch. The other side of the push-button switch goes to the opposite terminal on the inductor and also on the lamp. The lamp is in parallel with the inductor, which is an 8 Henry coil. Okay, when I push down on the switch, I'm applying 9 volts to the inductor and at the same time 9 volts to the neon lamp. The lamp does not light because it takes 60 to 70 volts to fire it. But when I let up on the switch, now the 9 volts is removed out of the circuit, so the only voltage source is the induced voltage of that coil, and the only path it has is through the neon lamp, and it is enough to fire the neon lamp, and it will actually flash that neon lamp, which would represent firing of the spark plug. Now, that switch, again, if you are an antique car buff and you want to go back into the prior to the 70s, would represent the breaker points that's on your distributor. Okay, the breaker points is that switch mechanism. It's actually physically a mechanical switch, just push button switch, but as it rotates, opens and closes. Now, if you want to advance up to the modern electronic ignition, that's that little box that says electronic ignition module, which is nothing more than a digital switch that's doing the same thing, and that digital switch is now what's doing the switching. Well, the advantage is there's not an actual mechanical switch that has contacts and a gap that breaks and corrodes and arcs across. So, but it is still nothing more than a switch. But I find students are quite interested in seeing this and actually observing it. And I tell them that if you don't believe me that we can get that kind of voltage out of that 9-volt battery, you're on your own. You put your fingers across where that neon lamp is, push it down. The 9-volt battery, you're not even going to feel that. Now, when you let up on it, tell me if you feel it or not. And some of them, you have to show them. Some of them, they have to try it. But everyone that's tried it, it's there. They say it feels like electric fence. So I think that's worked out to be a pretty good lab to show this principle. Okay, now let's look at this next circuit that we have. Now we've got a 36-volt source. I have a switch. R2 is 470 ohms, R1 is 100 ohms. I've got a 0.6 Henry coil, and R3 is a 20 ohm resistance. The switch is going to be closed at time of 0 seconds. So everything's based off of the instant that I close the switch. We want to know what VL, the voltage across the inductor, is going to be at time equal to 25 milliseconds. I want to know the voltage across the inductor at time equal to 1 millisecond. And the time for the current to reach 100 milliamps. Well, my equation for voltage for the inductor is E times, or this E, that's your applied voltage, times E raised to the minus T over tau. Remember, tau is equal to the inductance divided by the total resistance. Now, we're talking about the resistance in the loop that contains the inductance. In other words, your charging loop right here. This one's not included. So when we close the switch, we're looking at around this side of the loop. So my total resistance is R1 and R3 in this case, which is 100 ohms plus 20 ohms. So it's 120 ohms. So 0.6 Henries divided by 100 ohms, I come up with 5 milliseconds. Now we plug in 36 my source here. So it's 36 volts times E raised to the minus 25 milliseconds over 5 milliseconds, or raised to the minus 5. So that's 36 volts times 0.00674. So the voltage across the cap, 0.24 volts. And that's because my time constant is 5 milliseconds, and we're looking at 25 milliseconds. Okay, now B, voltage across the inductor at 1 millisecond, 36 volts times E raised to the minus 1 millisecond over 5 milliseconds. That would be raised to the minus 0.2. That's 0.819. 36 volts times that, 29.47 volts. So we see our decay rate is fairly rapid once we get here. We're looking at 1 millisecond, up here 25 milliseconds, and you can see the difference at your rate of decay. Okay, now looking at the time for the current to reach 100 milliamps. Well, I is equal to I max times 1 minus e to the minus x. Minus x is t over tau. Okay, so for the current for the inductor is equal to 300 milliamps. That's 36 volts divided by 120 ohms. Okay, that's 36 volts. We're looking at the 120 ohms here. Okay. That gives me 300 milliamps, just Ohm's law, times 1 minus e to the minus t over tau. And we know tau is 5 milliseconds. Put your 100 milliamps in here. Set this equation up. Set it up. We got 100 milliamps is equal to 300 milliamps times 1 minus e to the minus t over tau. Just crack through the math here, and we come up with 0.667 is equal to e to the minus t over 5 milliseconds. Here's where you're going to use that natural log again function. 0.667 is equal to minus t over 5 milliseconds. That will give you 0.405 is equal to t over 5 milliseconds. So that t would give me 0.405 times the 5 milliseconds is 2.03 milliseconds. So my current is going to go from the maximum current of 300 milliamps down to 100 milliamps in 2.03 milliseconds. Again, it seems very fast, but in reality, it's not zero time, especially whenever you start getting into digital electronics and the speed at which they're operating now in nanoseconds and milliseconds forever. So everything's relative. Okay, any comments to this point? Your students, I believe, can handle this based off of what you told me. And then the last slide is just the actual waveforms, and I've got a summary of both for RC and RL transient waveforms. Now, if you want to get real involved, you could actually have them graph some of these solutions with their graphing calculator, and they would come up with graphs that would look similar to this. I don't do that in the DC course. In the AC course, near the end, we have them graph a couple of them, but not in the DC course. Okay, any comments, questions? Give me a little feedback.
Feedback I can give you. No, this is good. Good to this point.
Is this helping?
Oh, immensely, Ken.
You're getting an idea of what the expectation is that they can handle these kinds of things.
Yeah, scope and depth. And what I'm seeing, what I'm really noticing here is that there's only a handful of my students that could go this deep. And I've kind of even prepped them to say, look, we covered the standards to a depth that lets me get you to a certain point. If you want the C-tag credit, there's another level of work that needs to be done on your end to get you there.
Mm-hmm.
And I mean that's just the reality. This goes far beyond what I think the standards imply.
Mm-hmm.
Not so much. You deal with the inductance and capacitance, but when you were talking mesh analysis and some of the other stuff last week, this I think is covered. But I don't know where. I don't know where to put it within the time frame that I have. Some of the depth you're talking here. So, but if they want the credit and they want to be they want to be I want the credit but want to be prepared for the next class. They're going to need to they're going to need to have this background. So. So great.
What we have to keep in mind is where the students are headed with this DC course.
Yes.
It's just like the example I gave with the last week when we were talking about the maximum power transfer theorem, which is coupled with Thevenin's theorem. If you're going to go into controls, if controls, automatic control systems and control loops is your area, we use that along with the bridge circuits all the time. And because to analyze and matching the impedance of the load to that of the amplifier to get maximum power gain, and then the idea of the balanced bridge circuits, and that's the basis of our control loop. That's really intensive that the student's going to be using that. And of course, remember that the DC course, this is your foundation level course, so you got to have exposure and understand it. You may not be 100% proficient at it, but you understand it pretty well.
Right.
Tonight, when we get into capacitors and inductors, especially if you're looking at the electromechanical side, and you're going to get into industrial motors and motor control, which gets into power factor correction, leading, lagging power factors, and all of that. They've got to know inductors and capacitors inside now. And so this is the foundation course. This is the basic tools that you're going to use. And then when they get into these more specified courses, they're going to keep, practicing doing this. But everybody needs this basic understanding of all these principles.
Sure. Well, everybody going into electrical engineering, electromechanical engineering. What other kind of majors would this be applicable toward? This DC course and really the courses you're offering in the 4 of them.
Well, it could be instrumentation, an instrumentation technician, Some schools have then you've got the electromechanical, the electrical. Computers, somewhat, but again, not as much perhaps.
Maybe computer engineering.
Yeah, computer engineering where they're designing, but if you're just looking at computer, when you just say the word computers, I mean you could be talking
programming.
Programming. Yeah, programmers they don't need this near as much. But if you want to actually design, work on, build, design computer systems, and get into the hardware side of it, the architecture of it, then you're going to need that.
Some of my former students were at Purdue, they're chemical engineering majors, and they have to go through this for Purdue because they do a big thing on electrical chemical in their engineering program.
Okay. That's good. No, I've mentioned it before. My background's robotics, and it's interesting. I never, getting my degrees are kind of around that, and I don't have a strong electrical background. I don't think I took a college class in electronics. And honestly, I haven't had to use it in 16 years of robotics, so there's a lot there's a lot more that I don't know than I do.
Oh, I don't disagree. I'm a journeyman electrician, journeyman wireman out of IBEW. I haven't used this since I was in my apprenticeship, just for classes. In the field, well, some of it I used when I was doing fire alarms, but not to this depth. It was all simple plug-and-play stuff.
Well, because a lot of this is circuit design, which I imagine is much more, I don't know, much less prevalent maybe than it used to be what do I mean by that? I guess circuits are getting so complicated these days, and equipment is getting so complicated these days. I don't know. Are there? Would you say there are fewer people that know the depth of this, or that have to interface at this level, Ken?
I think the need is for people with this knowledge. I'm concerned that it's drying up because what's happened is the old guys like myself are retiring out, and and again, I'm not claiming to be an expert in all of this. I learn something new every time I deal with it, but a lot of what I'm finding in the past 10 years or so, after using it in industry for quite a while and then teaching it for over 30 years, it's like, as I'm doing it, sometimes in working a problem on the board, it just hits me like a hammer in the head. That's exactly why that is the way it is. Where before it's always I've just been preaching it. That's the way it is, and that's and now it's like it's finally sinking in. Why couldn't you see that 20 years ago? But I'm finding that the new generation coming up is so reliant on computer apps. All I do is pull this app down and plug in all the data and push the go button, and it does it. And for them to actually be able to understand how to do this, I find a lot of them are lacking.
Sure. No, certainly that speaks about our youth and what we're seeing.
And a lot of it is the shift has been in the education world has left. It used to be you didn't have such a broad knowledge, but you really had a depth. Okay, and maybe it was a little bit too much that. Okay, well, the other side of that pendulum is we've got a real broad knowledge and no depth at all, And I think maybe that's where we're almost at now.
That's where we've pushed things to, yeah.
And to me, what we need is somewhere in between those, somewhere in the middle. You know, maybe not quite as much breadth, but more depth than what we currently have.
No, I would agree with that.
And you think about it, we'll just take motors. You know, the basic electric motor hasn't been around that many years. You know, and you go back to Edison's time and so forth, and all the development there, and Tesla and so forth with their the idea of the electric motor, and Westinghouse is another one that was in there, and how we generate power and so forth. That's not been around very long. And those guys knew all this stuff forward and backwards, because they're the ones that developed all.
Sure, they had to, right? They were figuring all this stuff out.
Yeah. And of course now, you know, we loop that in with automatic controls, and like the idea of power generation. It used to be that you know, your power engineer, basically what they were doing, you were constantly monitoring your load at the power generating plant, and you were constantly adjusting the biasing voltage across the field in order to your excitation voltage, in order to maintain constant voltage to match the generator to the load. Well, now it's all done automatically. So you don't have a person who's physically doing that anymore, but you got to have people that understand this is what's actually happening.
Sure.
And then you've got to have another group of people that understands how this automatic control loop happens to get the signal of what I need and compared with the signal of what I'm putting out. And the two have to be able to work together.
Sure.
Communicate with each other.
And we need that more and more.
Right.
We need more and more of those individuals as we become more and more of an electronic society.
Exactly.
With everything going on, sure.
I mean, just look at your car. I mean, now we got computers and everything else underneath the dash. You didn't used to have that. You know?
Yeah, that's right.
And you know, it used to be in order to tune up your car, you had to be a pretty decent mechanic. You had to have some understanding of what electrical components is used for the ignition, which is your coils and, you know, what we talked about, inductors and so on. And that was about it. But now you've got complete automatic control loops, you've got computerized sensors and all of this, that you have to know something about all of that in order to get your car to run. And it didn't used to be that way. And that's just one example. Everything is that way.
No, that's absolutely right. Hey, guys, unfortunately, I gotta get going. I